My topic is nuclear reactors and their physics. It's an exciting invention of the 20th century. And nuclear reactors are used mainly for electricity production, ship, submarine propulsion, and isotope production, etc. But we will concentrate only on reactors which are used for power, that is electricity production. Presently, 440 power reactors are operating with a capacity of about 390,000 megawatt electric worldwide. And in India, about 23 power reactors are operating with about 8,000 megawatt electric capacity. And reactor physics, which I will give you a small outline, is a field, applied field, developed after 1940. This is the lecture summary. You need not look at the slides, the numbers. So I will start with the first reactors, then a small introduction to atomic and nuclear physics, nuclear stability, nuclear fission and energy release, neutron-induced fission, characteristics of fission, breeding of fuel, chain reaction, and controlling the chain reaction in criticality, reactor types based on neutron energy, components of reactor, power reactor types, reactors in India, fuel breeding and fast reactor fuel cycle, reactor and fuel cycle physics, reactor physics theory. All will be in very briefly presented. Topics in reactor physics and one example, and then a summary. So we start with the first chain reaction, which was set up by E. Fermi in Chicago in 1942, which used the uranium metal fuel, which used low energy neutrons, which has higher chance of fission. We will come to this. We are just jumping little here because graphite is used as moderator for slowing down the neutrons. And this reactor was called CP1. It was cooled by air. And the reactor operation was controlled by absorber material cadmium. The picture of the reactor is here. The first reactor in India is Apsara, and the first power reactor in India was constructed in Tarapur. So I am just showing two reactors, experimental reactors in India. First is the Cyrus reactor, which was July 1960, 40 megawatt thermal power, and it used natural uranium fuel, heavy water, and water cooling. And another interesting reactor in Kalpakkam. This is in Mumbai, BRC. This is in IG car Kalpakkam. Kamini, which is a 30 kilowatt thermal, which became critical in 1996, and uses U-233 fuel. And you can see here, I don't know whether you can see it, the fuel plates can be seen here. The reactor can be, you can go into the top of the reactor and view the reactor. And this is the reflector blocks surrounding it. And the picture of the reactor can be taken while in operation. So you can see the Sarango, what you call radiation inside the reactor core. Now a small introduction. Actually, Dr. Nema and Dr. Vaidya also has given a small introduction to these things. But it is that atoms consist of electrons, protons, and neutrons. And example of hydrogen where one proton surrounded by an electron. Helium has 2 protons, 2 neutrons, and 2 electrons. Lithium has 3 protons, 4 neutrons, and 3 electrons. Uranium has 92 protons, all are not shown here, 143 neutrons, and 92 electrons. So Z is used for the electron and proton number, N is used for the neutron number, and the atomic number is the summation of N plus Z. This is important for us in this lecture, the energy. So in atomic and nuclear physics, the energy used is electron volt. 1 electron volt in more familiar unit is 1.6 into 10 to the power of minus 19 joules. And 1 MeV is 10 to the power of 6 electron volts. If you want to compare with some other things, see, microwave radiation has energy of 10 to the power of minus 5 eV, which we are using for TV transmission, etc., and mobile. Light has energies in the range of electron volt. X-rays are in the range which are used for medical purposes in the range of kilo electron volt, and gamma has energy of million electron volts. All these are electromagnetic radiations, and power is energy per second or watt. So 1 joule per second is watt, and 1 megawatt is 10 to the 6 watts. And atomic mass units is one mass unit is 1.66 into minus 24 grams, very small value. And so one proton mass and neutron mass are about 1. And one electron mass is 1,800 times smaller than this. So to understand what is joule, so 1 joule is the energy which is required to lift 1 kilogram of mass by 10 centimeter. And 1 electron volt is the energy gained by electron when it accelerates through 1 volt, because electron is attracted to the positive terminal. So this is the 1 electron volt. Two important numbers from which is remembered by all physics students is the following. That is, if you combine a proton with an electron, you get the hydrogen atom, and 13 eV of energy is released, because as the binding energy of the electron with the proton. These are the typical energies of chemical reactions. And in the nucleus, if you the simplest system like this is the proton and neutron, and which forms the deuterium nucleus. And if you form that, about 2 MeV, million electron volt of energy is released. So these two numbers are quite important. Einstein discovered that the energy and mass are can be converted from one to other. So the mass of m is converted to energy. You get energy equal to m into c square, where c is the velocity of light, which is 3 into 10 centimeter per second. So mass of neutron and proton is nearly 1 AMU as doing mass unit. And if you convert this using this relation, you will get 931 MeV. And 1 MeV is equal to 1 into 10 to the minus 13 AMU. Mass of the mass of hydrogen atom is slightly less than the mass of proton and electron by this very small amount of 13 electron volts. You can convert it to the mass unit. Similarly, the neutron mass is significantly less than the mass of the proton and neutron. This mass difference is called the mass defect, and also called the binding energy. And this energy is which is getting released in the fission, which we will be discussing now. So it turns out that as the different nuclei starting from hydrogen go like that, higher and higher, the binding energy per nucleon increases initially and then decreasing. And the maximum is reached at about that's atomic number is equal to 56. That is 8.79 million electron volt per nucleon. And this reduces to 7.6 MeV per nucleon at the uranium nucleus. So this is the reason for the energy release in nuclear fission. So the radioactivity of nuclear, which was nuclear and discovery of neutron and discovery of fission, were discussed by Vaidya in the last lecture. So the fission is the breakup of a nuclei into two nearly equal mass. Generally, Z is equal or less than the neutrons, number of neutrons in the nucleus, except for hydrogen, where it is equal. Nucleus becomes unstable if N is less, that is, the neutron number is less. If the neutron number is less, the proton inside undergoes a beta plus, that is the positron emission, which is a antiparticle of the electron, that is, it has a positive charge, and becomes neutron. And if neutron is more than required, then the neutron undergoes a beta minus decay and becomes a proton. It is found that heavy mass nuclei, when n by z ratio is more than unity, with mass greater than 105 may undergo alpha decay. That is, one helium nucleus itself can be emitted. Even heavier nucleus, that is like thorium and above, can undergo spontaneous fission. That is, fission is breakup of a nuclei into two nearly equal mass. So this spontaneous fission is found to occur for masses above thorium. Naturally occurring uranium contains 0.7% U-235 and 99.3% U-238. It can be found that U-235 undergoes fission relatively easily when bombarded with neutrons. This was the first way in which the fission was discovered. It is found that neutron absorbing U-235 forms U-236, which is a next isotope of U-235. U-236 is formed in the excited state, and binding energy of the absorbed neutron is available. This excess energy helps U-236 to undergo fission. However, other reactions like scattering, radioactive capture, end-to-end reaction are also possible in U-235. So assume that now out of all these reactions, fission takes place. The product nuclei are more or less more stable than U-235, as the binding energy per nucleon is higher for lesser mass. So stability of smaller nuclei results in release of energy. So this can be calculated. So here Dr. Vaidya in his lecture had shown a binding energy curve of a like an elephant, now elephant shape. But now this is the reverse. Here I am plotting the mass defect per nucleon. So when uranium 238, 236, 235 becomes U-236 and fissions into two masses of 118. So you get a positive energy, because here it is the mass binding energy is only minus 0.00814. Mass defect is only 814, and here it is 914. So this much gap, that is this whatever gap you see here, this much energy becomes 0.001 AMU becomes available as energy, and that multiplied by the 931 MeV per AMU, you get 220 MeV. So this much energy can be released in a fission. So heavy nucleus splits into two smaller nuclei, 200 MeV energy is released, and if you fission 1 gram of uranium fully, that is equal to energy of complete burning of 3 tons of coal. So this is the kind of factor difference. So that is why the nuclear reactor came into existence. So I am here, that same process is being shown here. Neutron being incident on the nucleus, neutron absorbed, deforms, and fission fragment is formed. That is the two equal mass, nearly equal mass nuclei. And then 3 neutrons are also emitted. So this is shown pictorially here now. The nuclear fission process, we can see here, U-235 nucleus, neutron is getting incident, and the deformed nucleus is formed, U-236, and it deforms into a dump shell shape and explodes. So you get 2 fission products, energy and neutrons. So the characteristics of fission are that fission fragments of atomic number A range in the range 65 to 170. They are not exactly equal, but in a range with kinetic energy of 170 MeV are emitted. Beta and gamma, that is the radiations, are also emitted. 2 to 3 prompt neutrons in the energy range 0 to 10 MeV are also emitted. Total gamma energy emitted is about 15 MeV, neutrinos about 10 MeV. So if you add up this, you'll get more than 200. Neutrinos alone escape because they don't react with matter. So the isotopes which are easily fissionable are uranium-235, plutonium-239, plutonium-241. I will not go into the reasons for this now. And there are some nuclei like thorium-232, uranium-238, Pu-240. They can be fissioned by high energy neutrons, but can be converted to fissile by neutrons of all energies. So this, what happens in a capture of a neutron in U-238, mostly. So it can fission also, but mostly what will happen is U-239 get formed, decays to Neptunium-239 and Plutonium-239. So this is a new fissile material getting produced, man-made fissile material getting produced. And thorium-232, similarly, can absorb a neutron, go to thorium-233, protonium-233 by beta decay, and then another beta decay goes to uranium-233. So this is the process by which new fissile material can be made. So this, you realize there is a scientist realized that extra neutrons are produced in fission, and a neutron-induced continuous chain reaction is possible in fissile material. But minimum one neutron must be available after losses in capture, because one neutron is required to maintain the chain reaction, and some neutron may leak out. So in a critical state or constant power production, this minimum one neutron should be available. When net neutrons available is more than one, the neutron population and power production increases exponentially, and this is called supercritical reactor. And when net neutrons are available is less than one, it's called subcritical. So here that chain reaction is just shown here. That is a U-235 fission. One neutron goes another fission. Here another fission like that. So this constant rate of fissioning can be maintained in some cases. So this uncontrolled chain reaction, which is called the nuclear bomb, which was made subsequent after CP1 was made, a nuclear bomb also was made, which maximizes the energy release by maximizing supercriticality and also minimizing the duration, that it should be as fast as possible. So the explosion takes place. So this is a nuclear bomb. The control chain reaction, which we are interested more, by use of neutron absorbers, exactly one neutron is made available after every fission event for continuous chain reaction. So steady state reactor power operation with constant power is possible. The power can be converted to electrical energy by heating a coolant and finally producing steam. So what are the nuclear reactors possible? So low energy neutrons interact more with nuclei because of the low energy of the neutrons. And this is a quantum mechanical effect. What is known as the wavelength of the neutron becomes large, and it spends more time near the nucleus, and so it interacts more. So it is found that the criticality can be maintained in natural uranium, that is 0.7% U-235, remaining U-238, provided the incident neutron energy is reduced by a moderate material like graphite or heavy water, which don't absorb neutrons, but when neutrons collide with the heavy water and the graphite, the energy of the neutrons reduce, and then they collide with U-230 uranium and produce fission. In a uranium metal which is used for a bomb, for example, where it is enriched more than 90% U-235, supercriticality is possible and neutron energies are maintained high. Here the neutron energies are not small in the KeV range. Another system which is the most common is the uranium enriching U-235 by 2 to 5%. Then uranium and water is used as the moderator to reduce the energy of the neutron by collision, and this can be made critical and can be used for reactors. So when the fissions are caused mainly by thermal neutrons, that is energy of 0.01 to 1 eV, see the temperature T is in Kelvin is 293 K at normal temperature, 20 degrees centigrade. If you use the Boltzmann constant, we can get that 3/2 kT, that is the thermal energy, as 0.04 E. So this is the range of the thermal neutrons, and they obey the Maxwell-Boltzmann distribution energies, and they are the fissile fission causing neutrons in the thermal reactors, that is the heavy water reactor which I mentioned just now, or the light water moderator reactor which I mentioned just now. Fast reactors and are where the 90% of the fissions are caused by neutrons of energy above 10 keV. There are no moderator like water or heavy water or graphite in the reactor. So these are the just whatever I have been saying in a summarized way. So there is a reactor here, which is contained in the vessel, and it's a shield, and there are reflectors around the reactor, and there is a support structure in which fuel rods are kept generally. Coolant is flowing surrounding the rod, and so the nuclear fuel element and clad, coolant, neutron moderator. So this coolant itself can act as moderator, or there may be external moderator. That is, sometimes water coolant is there around the rod, and then graphite can be the moderator. Then a reflector and blanket. Reflector for reflecting the neutrons, blanket in the found in fast reactors for breeding the neutrons, that is new fissile material. Then support structure. Then requires sensors, because you want to control the chain reaction. You want to know what is happening in the reactor. So you have sensors inserted into the core. And then there are safety systems for shutting down the reactor. That is, in case you want to, because the chain reaction is going out of control, then you have to shut down the reactor. That alone, see the reactor, it is operating for some time. It is having radioactive material. So even if you shut down the reactor, that alone is not sufficient. You have to remove the decay heat also. It is the heat generated by the fission products. So these two aspects are very important. So the active core, where the fission chain is sustained, moderator, where the function of the moderator is slow down high energy neutrons by elastic scattering. Moderators are materials consisting of elements of low mass number with little tendency to absorb, capture neutrons. And heavy water D2O, light water, beryllium oxide, graphite. Reflectors also similar to the moderator. They decreases the loss of neutrons by reflecting them back to the core. Heavy water, beryllium oxide, graphite. Blanket for production of additional fissile fuel like thorium-232, uranium-238 used in fast reactors. Coolant for heat removal. Water can be used, heavy water can be used, carbon dioxide can be used, molten sodium is used where you don't want any moderator. Control materials which absorb neutrons, which have a tendency to absorb neutrons more. Boron is the most popular. Cadmium, gadolinium, water also absorb neutrons. Shield to reduce the radiations, neutron and gamma, to acceptable levels outside the reactor core. Steel, concrete, water, lead, etc. So this gives the somewhat what you call outline of the reactor. So now we go to the different combinations, power reactor types. Different power reactors are many are there in India also. So pressurized, it is called pressurized water reactor. So here the fuel is uranium and the coolant and moderator is light water, that is water. And pressure, this is also called VVER in Russia. And the Kodakkulam reactor is that type. Boiling water reactor, the first reactor to be constructed in India, Tarapur 1 and 2, as a water-cooled and moderator reactor, and has enriched fuel, about 2.4% enrichment. Pressurized heavy water reactor, which is the most common reactor system in India, which has heavy water coolant and heavy water moderator. And example is the MAP reactor. And I will just show you the list of reactors. Gas-cooled reactors operating mostly in the UK has a carbon dioxide cooling, graphite moderation, enriched fuel. Light water reactor, you can say this is the reactor where the accident took place, the RBMK reactor, Chernobyl reactor, which has a water cooling, graphite moderator. Here the accident took place because of inability to shut down the reactor. LMFBR, that is a liquid metal reactor, fast bed reactor, sodium cooling, enriched fuel, and it is one example is the fast breeder test reactor. So the pressurized water reactor, which is the most common system in the world, how the reactor core, vessel, the control rods, and this pressurized water system, and the water is flowing and removing heat from the core. And there is a secondary system, which is water is boiling, going to the turbine and generating electricity. And this is getting cooled by seawater generally, or from the river water. So this is the system. This is the pressure. This is a pressurized heavy water reactor system in India. So here the reactor is horizontal. There's no pressure for the reactor vessel, but tubes containing pressure tubes in which the heavy water coolant is flowing and going to the steam generator, producing steam and going to the turbine, etc. There are some 400 channels. Heavy water moderator is separately there. It is at low temperature, not at high temperature, not pressurized, and uses natural uranium fuel and heavy water moderator. And this is the fast breeder reactor. So under PFBR, under construction in Kalpakkam. So there is a sodium pool, and there is a reactor core which is very small here. Control rods are coming from top. Sodium is flowing inside the reactor core, going into the secondary heat exchanger, and hot sodium come here. There are three circuits. One is this circuit, then the secondary sodium circuit, and which is cooled by water. So this water cools the secondary sodium and then goes to the turbine. So this is a list of reactors in India. The first reactor was Tarapur. It started in 1969. Then Rajasthan 1 and 2. Then MAPS. Then Kaiga. No, Narora. Yeah. Narora came next. Then Kaiga. Then Kakarpar. No, first, I think after Narora it's Kakarpar. And then Kaiga. And so in Kaiga, there are 4 units working. And the bigger reactor, 540 megawatt, Tarapur 3 and 4, came in 2006 and 2005. And the very recent reactor at Kakapara 3 has been commissioned now and got 50% power. And it is this year. So this is a panoramic view of the Tarapur 3 and 4, 540 megawatt electric PSWRs. And this is the Kaiga power reactor site in Karnataka. There are 4 units, and unit 1 created a new world record because these reactors are fueled online. So it created a world record of continuous reactor operation. That is, reactor continued to operate for 962 days, and it was shut down for maintenance only after about 3 years in 2008. This is because this is the other reactor in India, which is the boiling water reactor. Tarapur, this is a picture of Tarapur reactor. This is the reactor core with the fuel assemblies, grid plate, and the water going in like this, boiling inside itself. and then steam separators are here, steam dryers, and the steam goes to standard. Here the difference. In all the other systems, the control rods were coming from the top, and because here steam is generated on top and it goes out, the control rods are coming from the bottom. So the question is now about the breeder reactor. Can reactor produce more new fuel than consumed? Yes, the natural uranium contains small quantity U-235, but large quantity U-238. How to use that? So in slow neutron reactors, that is the thermal reactors, scarce U-235 used as fuel. Abundant U-238 is not used much. In all reactors, U-238 can be converted to fissile using fissile fuel Pu-239, as we had given the chain that earlier. So next few slides will explain how fast reactor produce fissile Pu from abundant Pu through conversion. When conversion to fissile is more than loss of fissile, then it is called breeding. This conversion takes place in the PHWR, that is in the heavy water reactor also, but it is more in the fast breeder reactor. By proper choice of fuel material and design of reactor, it is possible to produce more fissile fuel than consumed. It's called breeding. So for sustaining chain reaction, we had found that 1 neutron is required. But for capturing fertile nucleus, 1 more is required. Then other processes are there. So the total neutrons produced per neutron absorbed, regeneration factor should be more than 2 if you want to reach breeding. So it is this eta varies. In the next slide, we will show for different nuclei. By a combination of U-235, U-239, and the fertile material, uranium-230, thorium-232, it is called, you can produce a breeder reactor. So you can see here, I don't know whether you can see it. U-235 picture is here. U-233 is here. The eta, there is a regeneration factor, the number of neutrons produced per neutron absorbed. For Pu-239, above 10 keV, the value is about 2.2. Goes like this, like this. So, in principle, it is possible to produce a breeder reactor above 100 keV. U-230 eta is higher than that of U-233 or U-235. In fact, at 1 MeV, it is about 2.8. So, the breeding ratio is the fissile mass produced by fissile mass destroyed, and breeding gain is breeding ratio -1. For a breeder reactor, breeding ratio should be greater than 1. So Pu-230 is the undisputed fissile nuclide for breeder reactors with fast neutrons. So once if you have, so what is the use of this? So once you have extra fissile fuel which comes out of the reactor, it can be sent to the reprocessing plant, and then the fission products and the higher actinides like americium, curium can be removed, and the excess Pu can be taken out. So this can be recycled. So once you feed the reactor, and if you have a reprocessing plant, then you can continue to feed the reactor indefinitely. So this is called as the closed fuel cycle. Closed fuel cycle. So reactor physics of this and fuel cycle physics, and what are its important characteristics? A applied physics field developed after 1940, it became mature with the release of the book Physical Theory of Neutron Chain Reactors by Weinberg and Wigner in 1958. If you look at the fuel cycle, the physics events cover a very small to very large time span. That is picoseconds, that is where the fission takes place, and to teraseconds, that is 10 to the 13 seconds, where the decay of the fission products are to be taken care of. So only cosmology covers perhaps more time period, that is time span than this. Just to show you I don't know whether it is very clear to you, this slide. So the fission takes place in 10 to the -13 seconds. the prompt neutrons are emitted in 10 to the minus 7 seconds. And neutron detectors which are put in the core has respond within millisecond or less than millisecond or a few 100 milliseconds, sorry, about 100 milliseconds, that is 0.1 seconds. Neutron reactor period, while that is when you are raising the reactor power, the reactor power is raised in about 10 to 100 seconds, it will double. So this is the reactor period. It is called xenon transient, which I have not explained actually. Refueling your reactor takes place in about 1 or 2 years at a time, once in or 2 years. A reactor life is about 50 years, and the actinides have to be taken care of for about at least 1 million years. So this is the kind of time span. So now I will go to the very small portion of this fuel cycle, this whole thing, which is reactor physics theory, which is, so to say, is my field. So finding neutron and gamma distribution in a core and reflector and shield materials as a function of space inside the reactor and outside the reactor. And neutron energy is 0 to 15 MeV and gamma energy is 0 to 6 MeV. And as a function of time. This is done by solving the Boltzmann neutral particle transport equation. And there's an approximate equation for this, which is called the diffusion equation. So this is the in one slide, what is reactor physics theory. So some topics in this reactor physics theory: solution of the linear Boltzmann equation, neutron and gamma transport. Only numerical methods are possible, because the complicated geometry of the reactor and complex dependence of the neutron nuclei interaction, that is how the neutrons react with different nuclei, like the fissile nuclei, curtail nuclei, moderator, shield, reflector. So this can be solved only by iterative methods, and that is numerical. Then another important is the safe startup, criticality, reactor experiments, and reactor operation. So here, detection, monitoring of neutron population, online and offline, measurement of coolant and temperature, coolant temperatures, estimation of operating limits of fuel, how the reactivity of the core is. I should not tell, there is the multiplication factor of the reactor is changing with time. So these are the startup required for a safe operation of the reactor. Then the shield, that is the public and the operator should be protected against the neutrons and gamma. So how to design the shield? So here also you have to solve that Boltzmann transport equation. Fast neutrons are found to be most difficult to shield. And shield design, not only for the fast reactor, for fusion systems, for even reprocessing plants, and the fuel storage and disposal for a long time. So all these places, the shield design is important. Time behavior neutron population. How? See, it does not always happen that the reactor operates steadily. It suddenly it can go into a transient, that is a suddenly increase in population or decrease in population. So how to monitor that? So this physics solution of a set of nonlinear stiff differential equations for time-dependent behavior with material property changes. This is important because when the power is going up, the temperatures of the reactive materials go up. So their property changes. That is called the feedback. So this has also been modeled. So this is the another topic in the reactor physics field. Nuclear evolution with time. That is, when you want to operate the reactor, the fuel is burning. So you have to keep track of that. And when you are putting it outside the core, it is cooling and decaying. You have to keep track of that. So this radioactive decay, their decay amounts, heat generated, all these are to be solved. So this is nuclear evolution with time. So the equation itself is not very difficult, but the number of equations involved and its time, certain equations, that is certain fission products decay within a very small time, certain fission products take very long time. So this is a complex, again, numerical solution problem. Finally, is the reactor safety, which I mentioned, that is ability to sense and shut down the chain reaction quickly. So this, because of the inability to do so, this Chernobyl accident took place. Other is the ability to cool the reactor even after shutdown by emergency cooling systems. This is the reason for the Fukushima accident, because the diesel generators, which were supposed to work after the reactor shut down, were flooded by the water and could not give power. And that is the reason for the Fukushima accident. So now I have just I have covered that is as a, you can say, outline of the whole thing, nuclear reactors and reactor physics. I will just show one example. That is one solution of the diffusion equation. Modeling of the core of prototype fast breeder reactor under construction at Kalpakkam. For power distribution with observer movement. 3D neutron diffusion theory, which has 40 million data points and 5 million unknowns. So this present laptop, it can solve this problem in 1 minute. So if you plot it in a 3D plot, it will look like this. So this one controller is in more. So no, one controller is out. Sorry, these are in control rods, and these out where this peak is there. So this is the picture. So I have come to the summary of this lecture. So energy release in nuclear fission explained, conditions of sustained chain reaction and criticality in reactor, and then the reactor types and components, that is the different materials used, and how the heavy water, light water cool, fast reactor, and possibility of breeding in the fast reactor, and the fuel cycle. Fuel cycle is a very difficult field because the building the fuel reprocessing plant is more difficult than the reactor. So reactor physics design problem and its important aspects, which I gave you one example. So on the whole, there have been 2 major accidents in the so many more than 70 years of reactor operation. Despite 2 major accidents, overall contribution of nuclear fission power to electricity production in the world is significant and it is expected to continue. So why it is so is, Bhabha had said, no power is costlier than no power. That is, if you don't have power, then that will be more damaging. And let APJ Abdul Kalam said, let us empower the nation with quality power. So that is, that is less polluting, so to say, power. So I just, as a final thing, recently one book has been published, which has been partly written by me, an editor also, which is Physics of Nuclear Reactors, published by Academic Press. So thank you.